Okay, so we have a problem here. So that we can say that I
So perhaps he'll have a couple of seconds added on board by referee Cumberland Sunset. That was a good match tonight. Some of us will have to do a quick recovery for their match in March, in the 11th of March, and there's still a couple of weeks before that match takes place against Sundowns, Hastings United.
whoever is listening soccer, you must stop that. Okay, now we have a problem. We can't use that. So let's say we can say v squared. We use the cosine rule. V squared plus e squared minus 2ve cos delta over xs squared. And so that is 440 squared plus 440 squared minus 2 440 squared cos delta over 25. And we know that the current is 50 amps. And then we calculate delta.
Sir,
Yeah.
that's the problem that I had with that formula. Like, where do you know when to use that formula? Is it because of the situation of E is equals to V at nominal, or is it because of you are working in infinite bus, or is it because of your beta is 90? Or what? Why?
It's because you don't know the angle. And you want to find that angle delta. So there's no other way that you fall back on your trigonometry. Because
It's because of what? We don't have angle.
yeah, you want to find that angle there of E. So now you've got everything except the angle. So you've got that, and then according to the cosine rule, that squared minus plus that squared minus 2 times that and that cos delta gives you the triangle third part. This is now almost IXS squared. Yeah.
Yes, sir.
So use the cosine rule. And all right, what we've done there, we've separated the XS from the current and put it underneath the equation, and then we can solve for delta. So whenever you see you've got a problem there, you either fall back on the cosine rule or the sine rule.
Okay. Okay, I think don't go forward with that question. It's fine. The problem I had is it was that formula.
All right.
Yes. And then let me give other people a chance. I still have other questions.
Seems like you're not the sharpest pencil in the packet, huh?
Repeat that again, sir.
I said, you're not the brightest star at the firmament.
I never be.
No problem. Just joking. Right, other people, good questions? Yeah. Otherwise, who was going to take over again?
Mr. Leroux,
Yeah.
so can you please do for us question 7 of in connection with alternators, because I'm a bit confused when it comes to the fact that we're given the per unit induced EMF.
Hello.
Can you hear me, sir?
Yeah, okay.
Yes. We're given the induced EMF per unit, and then we're also given the synchronous reactance per unit, and then and also the delivering power of the synchronous alternator. But now here it says that if the prime mover's output is increased by 2%, decide the percentage change in the power and the reactive power.
Yeah.
I'm a bit confused about exactly like how do we approach that? Because like now I know that we're given per unit and then we're given the fact that there's a percentage increase. But here with the prime mover's output, isn't it the generated EMF that we have? And whereas the delivering power is the output, the output that the alternator is giving us. So now I'm confused regarding the fact that when we're saying that the percentage change that we have to get here, is it for the induced?
Let me show you. P is EV over X sin delta, no?
Yes.
And it's given that it's 0.5
Mm.
and it's 1.4 times 1 over 1.2, no?
No, the reactance is 0.2.
Yeah, okay, sorry, 0.2.
Yes, and then E is 1.2. Whereas the power is 0.7 per unit.
Okay, all right. So 0.7 is E
Yes.
is 1.2.
Yes. Yes, 1.2.
1 and X is
0.2 at the bottom.
0.2 sin delta.
Yes.
All right, what did you give delta?
I get 6.7.
All right, 6.7 degrees now. All right, and then it's a 1% increase in the torque.
No, 2%, sir.
All right, so 2% increase in
Yes.
the torque means dP is equal to 2% of its previous value.
Mm.
So that's going to be 2%, 0.02 of 0.5.
It's isn't it 0.7 for the per unit of the power?
Sorry, yeah, 0.7. That is 0.014 now.
Yes. 0.02.
Now, for a cylindrical machine, Q is equal to EV over X of course delta
No?
minus V squared over X. Now, so we can calculate dQ with d delta, because that's must the change in, and that gives you minus EV over X sin delta, you agree?
Yes.
And therefore dP d delta is going to be this was EV cos delta.
Mm.
You agree? Now we say, all right, what is dQ dP? So that means it's minus EV over sine delta over X divided by EV cos delta over X, and that is minus tan delta. So what is that? That is minus tan of 6,7. Tan sine tan. So that will change by minus 0,117 times 0.1% times 1%.
Isn't it 2% increase?
One sugar. Yeah,
Okay.
1002. Shit, that's very small.
Mm.
And so it's decreased by 0.2%. 100 times. It's 0.2%. All right. This is more or less an advanced question.
Okay.
So now you're ready for the advanced questions. We have to think a little bit.
Yes, sir.
All right. Any other question?
I posted the question on the black.
On the what?
On the note.
Yeah. I haven't checked Blackboard. Can you say what was the question?
Question 3 under synchronous motors. He posted it on the chat.
Damn, I should fix this papers of mine playing through each other.
So the advanced question that you just did now, which question was that?
I don't know. One of the students asked it. I know this stuff. Right, just tell me the question. Let me see. Question 3. Just read it.
Okay, question 3 under synchronous motors, 3.1. A 2 kV star connected,
Yeah.
hertz, cylindrical rotor synchronous motor
Mhm.
with a synchronous reactance of 8 ohms per phase.
Yeah.
And it says here, when delivering 120 kilowatts, the efficiency is found to be 95%.
Yeah.
Exclusive of the field loss,
Mhm.
and the load angle is 13 degrees electrical.
Okay.
If the machine is connected to an infinite bus,
Mhm.
determine the load current and the power factor.
Okay. So
And then, okay, that's 3.1. And then 3.2 is explain the operation of a synchronous capacitor.
all right. 18. 120 kilowatt How much is that? 120. Yeah. 126. 316. They want to know what the current is now. P is EV over X sine delta. The 126,316 is 2000. That's 127.5 now. And 1154. 1154,7 times E over 8 sine 13. And then you can calculate. Let me just stop this. 8 times.
Sir,
Yes.
shouldn't you put like 3 on that formula? Or maybe divide that power by 3?
Yeah. Yeah, because that's the total power. No?
Yeah.
All right. And then the 3 comes there. All right, let me check. 126.316. Where do you get E2 1296? You agree?
Yes.
The second question was?
Explain the operation of a synchronous capacitor. So I
No.
assume that's in the.
Yeah, it's in the handbook, yeah. Just remember a synchronous capacitor, that means it must be overexcited. And therefore the current will be leading and therefore it is acting as a capacitor. Right, any other questions? I'm waiting. Oh no.
Sir,
If somebody else has a question, what's yours?
sir.
What's your question?
Oh, my question.
Hmm.
Exercise 2.2 in the book.
What page is it?
I'm looking at the page now. 91. Number 3. Sir, my question is that they said at the end of the question, they said mention the necessary assumption. So when we do the assumption like your E is equals to V, you treat it as you are in a nominal excitation. It gives us the torque. So is that the only assumption that we can make for this question, or is there any other one?
Oh, no, normally it's what conditions you should fulfill for them to be able to synchronize. E must be close. The rotation must be the same and all that stuff.
Oh, okay. And then number 2, when I was calculating, I didn't get the correct torque. So I don't know it's me or is there anything that I missed? So I would like if you can go through it. Number 2, exercise
Yeah,
2.2.
I've got it.
Sir,
I've got it.
I'm correct. Oh, you got it.
Yeah. All right, so what did you get for E?
Oh, let me check my answers first. What's that answer?
And remember, torque is P
I'll
pi
give you now.
over 180 EV over Z sine beta plus delta. Did you use that formula like that?
Okay, is this one? What's your exercise 2.2? Is this one? Yeah. So it's 1.305. Angle 13.977.
13.5, maybe 14.
12 is 13, yeah.
All right.
Put it 13, say 13. Yeah.
Okay.
Yes, sir.
What's
Mm.
the beta angle?
What?
Your impedance angle 4.18 plus J 39.78.
My beta,
Mm.
it's 0.4 angle of 84
Okay.
per unit.
Mm. So, did you use this formula? 2 poles, so it's 1. So that's going to be pi. Okay, and again, times 60 over 2 pi ns. Zero, 4.
Yes.
Like that. Sine 84 plus 13. And then you times by 60 divided by 2 by 3000. Is that what you've done?
Yes.
And what did you get?
I got 8998.679.
898. Oh shit, man. That was almost 9. You agree?
Hey, I don't know if I punch it wrong or what. Let me check again.
No, man. Just look at the answer there. 899.8. 898. It's almost 9. So it's fine.
Okay. And then say when they say power transfer, is that a developed power?
That's between the two machines. Then you say it is E V over X is plus X is of the motor, the sine, the sum of the delta. That is your transfer power.
Okay, I'm talking about the one for parallel machines. Exercise 2.3. When they say calculate power transfer of machine A, maybe when we talk about under alternators, parallel machines.
Yeah.
So which one is it? Power transferred?
Now, first of all, you have to calculate the induced EMF. No?
Yes, this one they said calculate your circulated current. After it's your terminal voltage. After they want your power transferred. But to get there, you need to induce EMF, yes. Oh, they give us the induced EMF.
Yeah. So then you can calculate the current there. And the power transfer is the power that's being sent between the two machines.
It's power developed. Yeah, it's power developed.
Yeah.
Can you go to exercise 2.5, number 2 and 3? Oscillation, the one for oscillation.
Yeah.
Yes.
Bless you. So?
Should I read it?
No, 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 I've got it.
Okay.
So then you're going to use equation 2.105. J over T.
Exercise 2.5, number 2 and 3.
Yeah, yeah. Number 3, you're going to use the formula T is equal to 2 pi J over T.
Sir, your voice, can you write it? Maybe it will be better. Number 3, T is equals to 2 pi
J
J, yes,
over T.
over T.
Well, that is your moment of inertia. That is your torque.
So, yes, I saw that. How do you get your J? The problem is to get those ones. J, because I saw that formula that it can work. But to get your J, I think is the problem. Because there is those long other formulas they used.
Yeah, yeah.
So how do I get my J and T? Talk. I will talk.
Yeah, J is your kilogram,
Because we have signed for.
kilogram per meter square. Okay.
Yes, sir.
So first of all, you've got to calculate your current.
So we can hear you.
I'm not speaking.
You are not speaking.
Yeah.
Okay.
Okay, I'll send you those 2 questions.
Okay, thank you. And then I want you to know, Sene, the difference between stator losses and copper losses. What's the difference?
Stator losses is the iron losses.
And the copper losses?
It speaks for itself. It's the winding losses.
Okay, when we talk like in generator, the one at the output, the one when you add, you say PD is equals to your power output plus your copper losses.
Yeah.
Yes. And then when we come to and then your the mechanical side, where you have your P in is equals to your P developed plus your losses. Those losses, you have stator copper losses inside them, ne? Your iron losses. Am I correct? Okay, then motor.
Where there?
About
page 68. There's your
page
power flow.
68.
Yeah, that's your power flow diagram for a generator.
Yes, I have it.
Look at it nicely.
What I wanted to know is that, say, when you go for motor, it's P in is equals to your P developed plus your stator losses, which is, you say, it's your iron losses.
Yes, and your copper loss.
Or now it's becoming copper, stator copper losses.
No, it's always there. Remember, that's in your iron part of the
Oh,
in your status. You put most of your windings. Yeah?
yes, sir.
And it's like that. And that's also losses in iron.
Which means
And the copper losses is losses in the winding.
this one.
Okay,
Say, mm,
you got it.
I didn't got it. The voice, like, I don't hear you very well. Can you repeat it for the last time?
It's like the iron losses in the eliminations of your stator.
Hmm. See, yes.
You see that? Iron loss is in
Yes, I see it.
it's like in a transformer. And then the copper losses is due to the windings.
Okay, so I got you, thank you. And then example 3.2, I'm done with that one, thank you. Example 3.2.
Where is that?
You are there already.
No, where is it?
3.2,
Page.
page 150.
Right. Yeah.
I want to when you start there, you added to your power developed with your mechanical losses. Why is that power developed or power delivered?
Motor is all right. 39. That's your input power.
Okay, it's the one that you give. It's input power.
Yeah. That should not.
It was not supposed to be your power output. Why you say it's input? So which means you are changing the statement, because your P in is equals to your power developed plus
plus your losses.
plus your losses.
Mm.
So now which means we're going to calculate our PD. So which means we minus these two, we don't add.
No.
This one it's your PSCU. It's motor. Yeah. P developed is equals to PD plus the stator losses. Also your P in is equals to your P
in.
out.
P in.
Plus yes.
To P out.
Plus your losses total. Yeah.
Plus your losses.
Hey, so why are you saying that one is P in? We're going to do what? Because now you added the two.
Yeah. Because now we want to know what is the input current. So the input.
But you said your P.
Your input current then must supply the losses and the output.
Yes, I get what you are saying.
All right.
Plus your losses mechanical. So I'm saying I get you say that one is P in. So which means now you added your P in plus your mechanical losses. You say they give you P developed.
Yeah. Minus losses.
Hey, you minus the losses.
Of course, if you've got the input to the machine, and then you've got losses, what comes out of your shaft? That is 29.84. Then you've got some losses.
So why did you add? In this case you add them yourself. You add those two. Why did you add? Take example 150. 3.21. You see, you add them.
Yeah, calculate the current.
Why did you add them, sir? Because you say this is your P in, so which means you calculate for P developed. This thing was not supposed to be your P out. Power delivered.
Yeah, that's your output power.
Yeah,
Right.
it's output, not out in. It's not in. It's power out.
Yeah, that's 29.84. Right? Now,
Yes, sir.
we had some losses to get there. And that losses was 3.73.
Yes.
So we must have more there, which is the input, which is the sum of those.
Yes. Then you have the two.
Yeah.
Then you get your power developed.
No, that's
After. Yeah?
mechanical losses.
Sir,
All right, yeah, that's
the one that you.
Sorry, developed power.
Sir, which means you give us the power developed, not, power delivered, not
Yeah.
power developed, which is your P out.
Yes,
The one
that's
that is
20
given 29 point something.
Yeah, that's your output.
Or it's delivered.
Yeah, delivered is calculating in the mechanical, yeah. Okay. I see your problem. Okay, so let me check. So the input should be 500 times I. So it's cos pi, ne? You agree?
Yes.
Now,
Yes, sir.
so if we